Hello everyone, I'm Moitreya Chatterjee, a PhD student from UIUC, and today I'm happy to present our work titled Visual Scene Graphs for Audio Source Separation. This is a joint work with Jonathan Leroux and Anoop Cherian from MERL and my advisor Professor Narendra Ahuja. In this work, we attempt to address the problem of visually guided audio source separation, which operates in the following setup. Given a spectrogram of mixed audio signal and the corresponding frames as input, the task is to predict the source-separated spectrograms of the audio sources. Such a capability is critical to intelligent systems which often need to draw meaningful deductions about objects in the scene by associating their visual appearance with their audio signatures. We study the task of visually guided audio source separation and present a scene graph-based approach called Audiovisual Scene Graph Segmenter (AVSGS) to a Saturn. AVSGS extracts mutually orthogonal subgraph representations of the scene that permit the decoupling of audio sources. Our model shows state-of-the-art results across two audiovisual datasets, including on a novel dataset of videos collected in the wild called ASIW. Here we show an overview of our model's architecture showing the two key components of the network, the visual conditioning module and the audio separator network. Given the frames of an input video, the visual conditioning module first constructs a fully connected graph with potential sounding objects as the nodes of the graph. These are known as the principal objects of the graph and are denoted by PI in the graph. Additionally, the node set of this graph is augmented by adding the context nodes corresponding to each principal object node. These are denoted by VPI in the graph. Next, a graph attention network with an RNN extracts an embedding of a potential sounding object from this graph denoted by YI. This is done by creating dynamic masks on the graph. This process is then applied recursively to extract the embeddings of other potential auditory sources in the graph as well. The audio separator network then uses these visual embeddings YI as conditioning information to a unit-style network that takes as input a mixed spectrogram and produces the separated mask as output. This process is then repeated for other visual embedding vectors as well. We train this model with a weighted combination of three key loss terms. The first one is orthogonality loss, the next one is a consistency loss, and the final one is the co-separation loss. We conduct experiments on two audiovisual datasets. The first one is the music dataset, which consists of 685 solo and duet videos of 11 musical instruments collected from YouTube. The next one is the audio separation in the wild or ASIW dataset, which we introduce as part of this paper. It consists of more than 11,000 videos collected from the AudioCaps dataset. Videos either have a single or two audio sources. Every auditory event is described by one of 306 auditory words and is grounded to one of 14 visual object categories. This dataset will be made publicly available. Here are the results for separating a mixture of single source audios. The results show a superiority of our method over competing approaches across both datasets and across a wide range of different metrics. Next, we show some qualitative source separation results both for single source videos as well as for multi-source duet videos. We thank you for your attention, and here's the link to our project page.